everybody. Hello, hello. Give everyone a moment to sit down. Yeah. My name is Rob Simmons. I go by Utkanos, which is duckbill platypus in Russian. If you speak Russian, there's a whole long story. Ask me later about why I have that handle. So today we're going to be talking about comparing malicious files. And right now I am an independent malware researcher, and I'm the former director of research from Threat Connect. So I want to focus the talk on a few problem statements. And the first one is, commonly known as the AV problem. So many AV companies have their own unique nomenclature. So when you submit a file to an AV scanner, or if the scanner finds a file on your machine, it will, if it detects that, it will return a result as to what it thinks that file is. And so that result varies across different scanner engines. It also has various unique nomenclature within one particular scanner. And so this presents a problem for using that data. So even though it's very low quality data, we can all admit that, but I'll show you a few techniques for taking that low quality data and kind of squeezing a little bit of value out of it. So there's also, this is a related problem, so the marketing problem. Marketing departments want to brand malware families. They want to brand vulnerabilities these days. These are for, to be famous for finding this first, or for clickbait. Who knows exactly what the specific motivation is there, but that collection of motivations, it's mostly driven by marketing. And that's how you end up with very cute names like rockets and kittens and bears and pandas and all that sort of thing. And then you end up with an additional layer of this where you have many, many, many different names for the same threat actor group. You have many different names for the same intrusion sets and the same TTPs, actor groups. And so it's hard to kind of pick these apart. And a little while ago, I was, I'm on Twitter a lot, reading following various folks. And Robert M. Lee posted this tweet, which kind of hones in on one of the reasons why, number one, you shouldn't really use these names. Because the names that you see that are the outward facing names, from a particular company, those are a superset, or a subset, I should say, of a larger set of just bins based on TTP, malware behavior, other indicators that are collected from that malware or the environment it's found in, all of these sorts of things. And so the criteria that company uses to make those bins is probably unknown to you. So you don't know how they're differentiating the different things that are coming in. So they might not know the identity of a particular file, but they'll place it in, a temporary bin until more knowledge is gathered around what's in that particular bin, and then maybe separating it into two different bins. And then at some point, one of those will get a more formalized name that they have honed in on an intrusion set or a threat actor, and it's very specific. And then, that would become one of those more marketing term names. So, as Robert Lee points out here, you should actually develop your own criteria for differentiating different malware files and how you cluster them, how you differentiate them, how you decide that they're similar or different, and make that criteria internal to your own investigations. And then you won't have to worry about coming up with names and using other people's names. You would then have a set of criteria. You could take a data set that some company calls X, X actor group or X malware family, and you can compare that to your own internal criteria and see if it lines up with some of the bins that you're already collecting. And so that's a better way to kind of deal with this. So there's also two separate problems. They're very closely related and these are related to the work that we do in Infosec and in malware analysis and reverse engineering. So the first one is the researcher's problem. So when a researcher finds a new file that they've collected from, wherever their collection systems are getting stuff, and they want to know what it is they're looking at, and they want to see, is there previous research on this particular file or malware family, threat actor group, etc., to determine, is this a new attack? Is this something that I should spend time reverse engineering and deep diving, and then perhaps publish information, publish a blog post, publish something about it, or share data about that particular new entity among the community? There's a related problem. So this is the incident responders problem. And they're doing many of the same processes as a researcher, but they have much less time. So they're under the gun to figure out exactly what this particular implant or binary that's been collected off of an intrusion is related to, what it is. And one of the reasons why they want to find files that are related to it or figure out the malware family is to see, is there research that's already been done on this? And as opposed to what the researcher wants to know, the incident responder actually wants to see research that's already finished, so they don't have to start at square one. They can actually build on research that someone else has done about a particular malware family or actor group, etc., intrusion set, etc. So those are the two. They're very closely related, and the solutions for them are nearly the same. So some of the methods here for sample identification. For sample identification, you need to just determine the malware family membership of a sample, if possible. You're not always going to be able to determine the malware family. You could be looking at something that's a new variant. It could be something that you've made a mistake and you might have mislabeled it as an incorrect malware family. But the goal is to determine the malware family membership of a sample. And then once you know that, you would hopefully have a larger set of samples. There are public data sets. There's one called the Zoo, which is hosted on GitHub. You can clone it. And VirusTotal has a large data set, various different repos, or you have your own data set. And what you want to do is take the file that you're looking at, that's the unknown sample, the one that you're analyzing, and then there are methods where you can compare that file to your repository and determine files that are similar or related in some of a various set of ways. So I'm going to start with the low-quality data that we were talking about earlier as far as AV scanner results. So if you take a particular file and you submit it to something like VirusTotal or TotalHash or the various online scanner engines where the file will be scanned against as many scanner engines as are configured there. And so you get a big pile of results. And one thing to note with the results is many of the companies that deploy, that write AV scanners, many of them actually share an engine. And so if your calculus is to figure out how many, what is the detection percentage, is this a highly detected piece of malware? Is it low detection? Knowing which ones are shared engines can help you correct for that data, because if you count all of these as 5 or 6 different scanner engines detecting this, you're actually going to throw off your results. It's really just one that's detected it. So shared engines are a problem. Another one is the development method for signatures themselves. So among AV scanner engines, they take different tactics as to what their signature set does and how it works and how it's developed. And so you have the generic signatures, and generic signatures could be easier to develop in certain ways, but they cover a large swath of malware, but they don't say exactly what it is. It will say something like generic, and then the other end is a very specific signature. So Microsoft is fairly famous for their signature set, and they get very, very granular on naming the thing that you have submitted to Windows Defender. So here's a set of vendors that have usable results, in my opinion. So Microsoft, ESET, Kaspersky, Sophos. They all have to different degrees, fairly granular detection results that will either give you a place to start, and then you can go look at the threat encyclopedias that they have, where you can search for the result that you've gotten and see if they have a little bit more information about it. So this is the technique I was just talking about. So boiling down the results from a pile of unusable, AV scanner results, boiling it down into something that you can use to go dig further into the literature and blogosphere and stuff like that to find research on a particular file. So as you can see, I've actually removed all of the generic results from this list. So this is this file, and these are the results. By the way, AV scanner results, you have to know the date of the AV scanner result because the scanner result can change over time as AV scanner engines update and change their, removing of false positives, changing of detections, improvement of signatures. So the signatures will change over time. So this is the signature set. What you want to do is make sure that you get the sneaky generic results removed. You'll find Zeus, Zbot, Zeusy. Those have kind of become generic results. It's very unlikely that something is actually Zeus anymore specifically. So if you're seeing something like this, it may contain some code that's a descendant of this. But these are, I consider these and a few others just generic results. So you want to remove those from your data set. And so as you can see here, these all have the same result. I'm going to count that B down in the end. That might just be a little bit of uniqueness that they've added to their own engine, but it is still a shared engine across those scanners. And then here we have Avast and AVG. They're reporting the same thing. That appears to be another shared engine. So after taking all of the commonalities from those results, you end up with two strings, two scanner results, isbar and simi. And, like I said, this is very low quality, but this gives you at least something which you can go to Google or go to a threat intelligence platform or go to a malware repository and search for files that match these and see, is this what I'm looking at or is it not? And, it can help you on your way to figuring out what you're looking at. So another identification method or framework for identification is MITRE ATT&CK. Who's familiar with MITRE ATT&CK? Awesome. Very, very good. So MITRE ATT&CK is a framework of categorization for adversary tactics and techniques, and it's an excellent first step. And I say excellent first step. It's actually very, very good for most of the things that you all are probably using it for now, which is adversary behavior on the network, pivoting, attack techniques, and such. But for malware classification, it's not ready for prime time, and it needs a lot of help. So there are the former MAEC. I think there's some. I'm sure you could tell me more about this, but I think there's a lot more additions that are being put into attack, including the idea of sub-techniques. So a technique is very generalized right now, and so you'll see in a moment some of the sub-techniques that I've actually identified and begun contributing to attack. So this is one specific one. So the granularity of attack in this particular analysis area is not there yet. But what you're looking at here is a structured exception handler. So is everyone familiar with a structured exception handler? There's a few. Okay. In most programming languages, I think most or all programming languages, you have the idea, and I'm a Python programmer, so I'll kind of give this to you in the Pythonese, but you have a try and an except statement. So you try something, and then if it fails for some reason and generates an exception, you would run code under the except statement. So in a Windows world way, in Windows compilers and SEH, what this basically does is the adversary creates a set of code that they know is going to generate an exception. So it will always generate an exception, and then their malicious code resides in the structured exception handler. So the binary will actually pass execution into the structured exception handler, and then all the bad things happen. And it's just an anti-analysis technique. It makes it a little bit more difficult for someone to just straightforward reverse engineer the binary and figure out where that code is actually located. But to set up a structured exception handler, the hint there is structured. So there are two components of it. You can see at the top there's SEH save, and then at the bottom there's SEH init. So anytime you set up a structured exception handler, you're going to find both a save and an init. It might do something slightly different in between the two, but it needs both of those to actually set up the structured exception handler. SEH save is always the same. So that's a single set of hex, which you can see starting over there, the 64, FF35, and a lot of zeros. So that's going to be the same across all structured exception handlers. But when I began looking at this, I always go out and look for folks' Yara signatures. There's a few large Yara signature repositories on GitHub, and they include techniques and stuff like this. And so I looked there to see what signatures were already available for detecting structured exception handlers, and I found, this right here is at least new to me. And I'm not sure if this actually is fairly common across some, malware families that I've found. I am not familiar with why this is different from the structured exception handler initialization that was already known. I think it might just be depending on what compiler you use as to which register it uses, whether it's EAX or others. I still need to research more on that to figure out why there's variation in this, but I found new variation in SEH init. So I took the signature from Naxonez, which is the author of the original signature, and added another variation on SEH init. And also up here at the top, I've begun putting attack techniques, tactics, and sub-techniques. Even though sub-techniques don't exist yet, I've begun collecting the sub-techniques that I'm contributing to the project, so I'm going ahead and tagging them in this way. So you'll see SEH init is the name of the rule. So if this matches on a file, Yara will report SEH init. And then it will also give you what's on the right side of the colon at the top. Those are just Yara tags. So it's free text. And so I've begun making Yara tags that match up with the techniques and tactics and sub-techniques in attack. And I recommend that if you've got a Yara signature set, this actually makes it very easy to track the various attack techniques. So also, I want to make sure that you contribute. So attack is it's a crowdsourced kind of thing where the people who use it need to contribute more information, data, signatures, signature patterns, and techniques and tactics to it. So please do that. And here's an example of an area where, it needs a little bit more granularity. So second factor interception, which is T1111, is very, very general. So a second factor can be intercepted in many different ways. And so I've listed here a few potential, and these have been submitted to attack as potential sub-techniques. So SMS interception on the wire. So this is basically a man-in-the-middle attack that's catching the unencrypted SMS from your bank or from whatever organization and using it before you're able to use it. SMS interception by number porting. This is where the adversary will figure out the phone number that you have your second factor token sent to, and they will port your phone number to a handset that they've purchased somewhere, and they'll be able to intercept your SMS, phone calls, and everything. So that's an interception method. Also, code interception via phishing page. So Nilefish and Charming Kitten. They, if you look on I don't remember the name of the research site out of the University of Toronto. I'm drawing a blank. Citizen Lab, sorry. Drawing a blank on Citizen Lab. But you can look at Citizen Lab's research on Nilefish and Charming Kitten about this particular technique. So this is essentially, they'll have a phishing page that looks like your login, but it includes the second factor token field. And so they are sitting on that phishing page and will use your second factor token immediately. So you type in your username, password, second factor token. That moment, they are using it to log into your account. So And then there's the lowest hanging fruit of second factor interception keylogger. And there are probably many more than this. And I would encourage you, if you can think of any more, please contribute them to ATT&CK. The next one is Malpedia. Is anyone familiar with Malpedia? Awesome. So Malpedia is, again, a repository of Yara signatures. And there are not only Yara signatures, but reference samples for various malware families, various threat actor groups, TTPs, etc. And so there are the samples that you can compare the file that you have to, and then there's a set of Yara rules. As you can see over here, so the status over there, there's a little yellow star, and then a green something or other, and a red tag. So not all of the entries in Malpedia are fully fleshed out right now. So again, please join the effort if you can contribute Yara signatures, or if you find a sample that you know is a particular family or actor group, and there isn't a sample available here, contribute that sort of thing to Malpedia. And this is what you get for using Malpedia. You can drop a file into Malpedia, and then it bounces that file across all of the Yara signatures in the encyclopedia, and then returns the % match and the number of strings matched from any of the signatures. And then it will return rule names from those particular signatures that matched. And then there's always Google. So I think most of us who became IT experts through this methodology, which is, after all of the other things fail, just Google it with a few words and then follow the directions of what comes back. So, any researcher, even if you have a file hash, Google the file hash. You'll commonly find that file hash showing up in VirusTotal. You'll have some VirusTotal pages. You might have hybrid analysis, any of the other sites on the internet that allow Google to index their sandbox results and other sorts of data. You'll be able to get that data, as long as it's not, right now, as long as Google has crawled it. So Google's always a good backup method to always hit. So I wanted to cover a few other systems. These are a little bit more esoteric. So there's the common malware enumeration. This is in that sort of same family of MITRE systems as CVE, etc. So common malware enumeration is an attempt to enumerate and differentiate different malware files. And then MAEC, malware attribute enumeration and characterization. This is a subset or component of STIX taxi. And so this is a way to represent things like sandbox results, or to represent dynamic analysis results, to represent reverse engineering results. And so it's a way to classify and characterize malware. There's also ICAR in the EU. The wild list, I put this on here. This is a very, very old system for providing a constantly updated list of examples of malware that's found in the wild, and then Caro. So that's a pretty good overview of the various classification systems that are available today. But I think we could do with something new, and I hate the idea of maybe we should have a new standard, because if you have a new standard, then you're going to have 10 variations of that standard, of course. So I don't know that I have the full solution here, but I can tell you from my background in biology already has for organisms a system of nomenclature, the Latin naming system, which does actually satisfy both the marketing problem and the nomenclature problem from AV scanners. So as long as you've got one single nomenclature and it's shared across different vendors, then you can actually have something that solves the AV problem. And then if you do something similar to the way that Latin naming works, the scientist that discovers that new type of shrew gets to put their grandmother's name on that shrew. And so you get the same benefit that the marketing types are looking for, which is, the cute name or the thing that you can use in your marketing material. So there is a concept that other disciplines have at least solved already. So for associations, and one of the main things that you're going to use for association, I know dynamic analysis is, in the level of difficulty. It's a little bit higher up in the level of difficulty. But static analysis, you have all the tools available to you, so you can gather a wealth of data from a file without even running it. So some hashes that you can gather from a file, which allow you to relate it to other files in your repository. SSDeep. So this is context-triggered piecewise hashing, also known in street slang as fuzzy hash. And so fuzzy hash basically, instead of taking a file and running it through a hash algorithm and arriving at one unique number or hash, which is different if you change one bit in the file, you're going to come up with a different number. This is slightly different. It takes a algorithm and divides your file into predetermined components and then runs a hashing algorithm on each one. And what this does is when you take two of these, you would then see how different and where that difference is between these two files. And if you think about it from a mathematics perspective, you've got you have a three-dimensional space, and then in the center is the file that you're looking at. So if you run that same file through the hashing algorithm, you're going to get the same hash, unless your computer is broken. But you're going to get the same hash. And then you have all the other files in your repository, and they are all going to have a different hash, and those hashes are going to be a certain distance away from the center. And so all of them are going to be some distance away, and SSDeep has a 1 to 100 scale. And so the stuff that's completely different out here is going to be at the far end of it. And so what you want to do is choose a threshold. So of all of the files in your particular repository, you want to choose a threshold where all the files that are within that edit distance away from the file that you're looking at, you would consider related. So it's a little bit of an art to figure out what that edit distance should be, depending on the type of file you're looking at. If you're talking about PE as opposed to Word documents and PDFs, etc. And import hash. So this is a different type of hash, but also very useful for finding related files. You take the import table of a PE executable and you create a hash of it. So you take that import table, which has the different functions that are imported for the software to use, and you take that import table, which can have a unique order of the imports, make a hash, and then as long as you've done that to all the PE files in your repository, you'll be able to find other files that have that same import table and are therefore likely related, or it would at least give you a smaller pool of files to sort through and figure out which ones are actually related and which ones are not. But both of these hashes do have some gotchas, and I want to cover the one main gotcha for each one when you're using them. So SSDeep just looks at the file itself. And many malware families will use what's called a packer, which takes the payload that actually gets run in memory and run on the target's machine, and it will either compress it, encrypt it, or use like an installer of some kind. It'll use a commercial installer, reuse that. And so when you're running SSDeep, you want to run SSDeep against the unpacked file, the payload, because if you run SSDeep in your repository and nothing is unpacked, then all you're doing is finding the similarity between the two packers, not the payloads. So that's a thing that you want to watch out for with SSDeep. Import hashes, one of the main problems that I've found with import hash is that you'll find .NET binaries. So if you're working on a .NET binary and you take the import hash and plug it into your repository, all you're going to find are thousands of other .NET binaries that have the same import table. So it's completely useless if you're investigating a .NET. So another wealth of data can be gathered using Exif tool. So Exif metadata, depending on the file type, will basically pull out lots and lots of different data points for static analysis. So this is a Word doc, and you have the modification dates. I understand that dates can be what's called time-stomped, which means the adversary has tampered with the timestamps before they deploy the malware. But it's good to gather that data anyway, even if it's time-stomped, because if they time-stomp in the same way across many files, then the fact that they're time-stomping in a regular way, you could actually use as a data point. So it gives you the MIME type, and down here at the bottom, in Office land, this is called author. In PDF land, it's called the PDF producer. This will actually be in a slide a little bit later on. But this is an artifact that's left by the editor, which edited the file. And when you first configure or install Office, it asks you what your name is. And whatever you type in there gets put in the metadata of all the files. So, commonly you can find at least a string here that could be unique and differentiate a particular Word doc from other Word docs in your repository. And the same thing, last modified by, it leaves a little that same string from another user. So if you pass the file to someone else, it will leave the last modified by from their name that's configured in their Office instance. Created date. And then code page, this is not a very interesting code page, but if you look at the code page and it comes up with a very unique or specific language, that's another good data point. Now I want to talk about code signing certificates. A few weeks ago, I gave this talk in BSides Ljubljana, and I actually misspoke and called them malware signing certificates. And so you'll see why in a moment. So what can happen is the file could be signed with a fake cert or a self-signed cert. So this is a certificate that has not been signed by a certificate authority. It could also be signed with a real or stolen cert. So it could be a real cert that is bought from the CA, and you'll see in a moment just how bad this is right now. Or it could be a stolen cert. So they have compromised a legitimate software developer, stolen the keys to their cert, and then begun using their cert to sign malware. There's also another kind of broker or cert service sort of thing in that area. In many areas of the world, you can find a company who will actually let you use their cert for whatever you want to sign. And so those usually end up being used to sign malware. You could also have a signed-ish or broken signature. So the signature lives in a directory called the security directory, image data security directory. And so that directory, even if it's, in my consideration, even if it's filled with gobbledygook, if it's not a real cert, I would consider that an attempt to be signed. And so whatever that data is in there, even if it's super malformed or just junk, the fact that that junk exists can be used to find other certs or other files that are junk signed in that same way. So I want to talk about abused certificates for a moment. So this is data from a malware family called FileTour. This is one that I began reversing back in January and did a deep dive into it. It's used by Eastern European, Russian, Ukrainian, and Turkish adversary groups. And FileTour is more of a TTP or a behavior or a tactic technique rather than a true malware family, because there's so many different actors that use this. What FileTour is specifically is InnoSetup, which is a commercial, it's actually open source, I believe. It's an open source packer for freeware people and commercial software people to distribute their software. So they'll make a legitimate application, and then they'll pack it with InnoSetup, and then that's the little setup program that you run, and then it says where do you want to install stuff, et cetera, et cetera, et cetera. So the combination of downloading malware or installing malware and using InnoSetup is basically FileTour. So that's that malware, that sort of pseudo malware family, or at least TTP. So from FileTour, this is I have a data set of approximately 25,000 files, and across those 25,000 files, I found 500 valid certificates signed by certificate authorities. So they are obviously the very lowest level of validation that's possible with the certificate authorities, but they are still signed by the certificate authority and have not been revoked as of when I looked at this. And the big offender would be Komodo, and then it's kind of a who's who on down. So 96% was signed by Komodo, and then you have Thought and Digicert and various other ones down there, and like the drill bit digits and single percentages. So in the next set of metadata is PE metadata. So you have sections, imports, exports, resources. These each come from different areas of the PE structure. So this is I know this is very hard to see, but this you can find if you just Google PE structure or PE specification, and you'll find this in the Google image search. So this is basically where in the order of a PE file, where are the sections, where is the header, where are imports, where's code. And so as you can see, what you can do is you can take that section, or you can take that resource. That data can then be run through a hashing function like MD5 or SHA-1, SHA-256. And then if you do that across all of the files in your repository, you can then do that to the file that you're looking at. And you can find other files in the repository that share the same resource, share the same imports, share the same exports, etc. And then that's a way that you can find related files and then kind of dig through the results. You may have, this is a fair, for some, depending on the resource and depending on the section, you could get a whole bunch of false positives, or you could get a small number of related files. So looking at sections, this is .reloc, and this is for this particular sample. And so if you use this MD5, you would be able to find other samples that are like this one that have this same section. Again, with resources, the same thing. RT version resource in this particular sample gives you a SHA-256 of that resource, which lets you then find files that share the same resource. So there are a couple of different algorithms that various folks have out there for finding related files. So Reversing Labs, they have a large data set of binaries. And so if you have a file, you can use the RHA to find other files that are related to that. And they nicely wrote a blog about what their methodology is behind how the Reversing Labs hash algorithm works. If you use VirusTotal, they have a similar sort of thing. It's the similar to index. And so if you take a particular file hash and you run it through the similar to index, it will return a set of files that Google VirusTotal decides are related via machine learning and some of their black magic algorithms and that sort of thing. So document metadata, as we saw earlier, some of the document metadata is very important. These are some of the most important. So author and PDF producer, those are the same thing, just the one is in PDF land and one is in Office. And then timestamps, language, all these can be used to relate files and find new ones that are related to ones that you already have. Now let's talk about dynamic analysis. So as opposed to static analysis, this is where you actually run the file and you observe its behavior. So one of the things, is anyone familiar with domain generation algorithms? So in the same sort of concept, the domain generation algorithm is going to generate a string each time, and that string is known. And so in that same way, the file names for some malware families will drop itself or drop payloads or drop different data files or various things, and the file names will be dynamically generated. And so if you can figure out what a regex for that particular pattern is based on their file name generation algorithm, you can potentially differentiate different malware families by the file name patterns that they're leaving on the victim's machine. I highlight here URL structure for download. This is just to kind of point out that this is very interesting. It's not actually related to the malware family. The structure of the download. So if a malware binary is reaching out to a infected WordPress or compromised WordPress site or Joomla or something like this, and downloading a payload from it, the structure of the URL on that compromised website is not necessarily related to the malware family, but it is related specifically to the vulnerability, usually is related to the vulnerability in the CMS. And so you can develop a regex for the various variations of that URL structure. So thinking about the URL structure for download, the C2 structure for URLs that malware reaches out to, that is directly related to the malware family. So many people maintain regex repositories of the, for a particular malware family. What are all the different variations in that malware family for its C2? And then you can take a new URL that you've got and bounce it against that set of regexes that you've developed or have been shared with you, and you can figure out potentially what the malware family is. This is an example of that. So this is more of this is actually more of a phishing attack, but I wanted to show you the idea of taking a particular URL and developing a regex from it. So this is Blogspot. This is a Blogspot malicious URL structure, and this is from an attack early last year against a set of journalists. And as you can see in the regex down at the bottom, there's a UID. And you don't see the UID in the URL here. I actually removed it because the UID is the victim's email address in base64, so I don't want to put any victim email addresses in my slide deck. So if you want to read more about this particular attack, this is a blog post that we wrote about it. And the reason why they chose Blogspot is it makes it easier to circumvent Google's protection against phishing and malicious attacks, because Blogspot is already a Google property, and so they're not going to the checks are not going to be as strict or specific for things that are already hosted on Google's infrastructure. You can also use mutual exclusions, so a mutex, as they're known. So this prevents a race condition if there's two processes running on a multiprocessor machine. They use a mutual exclusion so they don't, step on each other's toes as they're doing work. And so malware will actually it's a program, so often malware will use a mutual exclusion to do that. And so the string that it uses for mutual exclusion is often unique to that particular malware family. So whatever string the malware author has chosen could show up across various builds of their malware, and if it's reused in that way, you could relate those together. Same thing with the registry key. So as malware executes and is run, it goes through and does, deletes, modifications, additions to the registry. And so that set of registry modifications and keys that the malware has touched can be used to look to see, is there another malware file that looks at the same keys, or perhaps looks at the same keys in the same order. And so there's many ways that you can use the registry key set that a particular behavioral analysis comes up with, and compare those two and see patterns across different malware families. So let's go a little bit more complex and a little bit more high level here. Clustering algorithms. So there's many different clustering algorithms that you can use. And so a clustering algorithm takes a set of files that you've got in your repository and tries to determine clusters that are related based on that algorithm. So I highly recommend if you're interested in doing malware clusterization. So this is a workshop from Seb Draven. This is one that I attended year before last at BotConf, and it's all up on GitHub. It's a really excellent review of doing malware clusterization, and it's based on the zoo, which I mentioned earlier. So the data set that you need to do this stuff everything is out there in GitHub, and you can work through it on your own. So the algorithms that are used in there, k-means and dbscan, have various pros and cons. But one of the things that's really interesting about that is once you get through working through those that workshop, you realize you don't actually need a GPU, you don't actually need a lot of horsepower to do clusterization if you do clusterization smartly. So if you use I'm a biology major, so I'm not too heavily into the math end of this, but there's a difference between using a full matrix, which has, any of the empty slots actually have a 0. And so if you use a sparse matrix as opposed to a full matrix, you can use a computer like this rather than a supercomputer to analyze the matrices. And so you'll find out if you go through that whole process there, that it's quite easy to use those algorithms on even a machine that has the horsepower of this guy right here. I want to have a pause here and point out a friend of mine and colleague, Tony Gidwani. She has a Infosec Finer Things Club, and so please follow this Twitter handle. And she works on malware research and wine pairing. So what wine goes well with certain malware and malware research. So one of these fixes everything, and the other is a roll of tape. And that's the Infosec Finer Things Club Twitter handle. So please give it a follow. Next method that I'm going to talk about is the diamond model for intrusion analysis. So I'm not going to go into too much detail here. In a couple slides, you'll have a link to go read the paper itself and kind of go into complete detail there. But I want to show you a graphic from my old team that we developed. And so you'll notice that we use the diamond model to analyze Star Wars. And so you notice this is a little bit of an inside joke, but the victim is actually the Death Star, and so the adversary is Luke Skywalker. Because it's all it's based on intrusion analysis, we kind of had to make the Death Star the victim because that's the appropriate thing, the appropriate configuration there for Star Wars. So this was actually almost a knockdown, drag-out fight in our team because we disagreed on whether proton torpedoes were capabilities or whether they were infrastructure, and various different pieces. That was a fun discussion. But this is the diamond model paper. Please go download it, read it, implement it in your programs. It's a very good way of taking a pile of unrelated data or seemingly unrelated data and creating nodes, basically creating nodes and groupings, and then relationships or edges between those nodes. So another association method is Icewater. So this is a website, icewater.io/search. You can take a particular MD5, SHA-1, SHA-256, and you can plug it in there, and then you can find, based on the clusterization algorithm in Icewater, you can find other files that are related to that within a particular cluster, and then you can see the orange clusters are 1-bit difference in the cluster ID, and then the green up there is a 2-bit difference from the cluster ID. And so you could find clusters that are in some way near the cluster that you're looking at, and if the file is within this cluster, you could perhaps find other builds of a malware family or files that are related to it. You also get this graphic of the file, so it presents what the file looks like in a graphical sense, and a few data points that you get down at the bottom, the hashes, etc. So the next thing I want to talk about is control flow graph analysis. So is anyone familiar with control flow graphs? Control flow graphs? Awesome. So a control flow graph is essentially if you take a program, PE binary or any any program out there, you're going to end up with blocks of code, and then a block of code is linked together with all the other blocks of code in that particular file, and they're linked together by if-then statements, or they're linked together by loops. And so if you take the whole set of blocks and all the ways that they're interconnected, that is a control flow graph. And so the control flow graph of the code that's inside of a Microsoft library is not important. We don't care what the control flow graph is in there. But if you take the code that was written by the adversary, the control flow graph of that adversary code could be the same or reused in other malware that particular author has written, because everyone reuses code. You might cut and paste a particular stretch of code, paste it into something else, and then you're going to end up with a piece of control flow that matches that particular little section of code. So this is a really good introduction to control flow graph analysis. This is Bert DerbyCon from 2014. And this is the YouTube video. I highly recommend watching this. This will give you a very, very good understanding of control flow graph analysis. If Iron Geek's camera was slightly to the left, you'd see the top of my head in the front row. And so this is a control flow graph from Redare. And as you can see, those are the different blocks of code. And then you'll see green and red, whether the if statement is satisfied or not satisfied, and then loops that go back to the top of a particular block of code. Also, of course, there's goto. So there, that is another control flow method. So there could just be something like that just goes off to wherever you want it to go. But for the most part, it's if then and loops. The last analysis technique I'm going to talk about is graphing your threat data. So this is something that I have been doing deep dives into recently, and this is something that is very, very, very powerful for looking at threat data. So everyone's familiar with the STIX schema, and if you think about it, look at the ones on the left. Those are STIX domain objects. And then the ones on the right are STIX relationship objects. And so in graph theory, you have nodes and edges, and so this lines up perfectly with graph theory. The nodes are your STIX domain objects, and the edges are your STIX relationship objects. And you can even see that, many of the relationships or edges between the nodes even have, as graph theory refers to it, directionality. So you can have bidirectional relationships, edges, or you have unidirectional edges. And when you're working with graphing data, you need to have it in a format that is conducive to doing graph work. And so these are two. I recommend RDF because it's the native format that my favorite graph database, which you'll see in a moment, uses. You could also use JSON for linking data. JSON for linking data, if you're not familiar with it, it is JSON that has a little bit of syntactic sugar that's been added to it to understand relationships between the key values in JSON. RDF N-Quad is not quite as pretty and human readable, but is as powerful. You can see these. So I've actually put spaces in there. You don't have to have spaces, but it the spaces in between those blocks of text. Each one of those blocks of text is a node, and then you'll see the edges are the ones. So in the top, there's actually 3 edges. One edge that leads to setup, one edge that leads to mfam, and one edge that leads to imp hash. So, and I'll give you an idea of how this actually looks. But there's 2 main graph databases. We can have a discussion on which one is best after the talk. But my favorite is dgraph. Neo4j is, an older database, but dgraph basically starts from scratch. They're based on some of the same research and people that built the graph database inside of Google, and this is their own separate company now. It's basically a key value store called Badger, and then a relational layer on top of that of ways to relate the different key values. And if you want to get into graph theory, I recommend Introduction to Graph Theory by Richard Trudeau. And then this is what you end up with. You get a network graph. So this particular network graph, this is very simple. The yellow, you can see there, those are two files. And then the blue is they're related to each other via import hash. So the import hash becomes a node, and then the files are two nodes, and then the edges are the relationship that those two share that import hash. You can get even more complex and even more complex, and if you graph all of your entire data set, you can then kind of play around with the graph itself, and you can get some kind of emergent properties that kind of a person would be able to see, but maybe a machine might not be able to see certain relationships. And then you can also use mathematics to find relationships between the files without actually having a person playing with the graph. But as you can see here, the blue again is an import hash. The green there is actually the malware family name, and then the red are the file names. Any questions? No time for questions. Come outside and ask me questions.